Now we're going to try to solve that problem. Hopefully you made some progress on it. So the inlet Q dot is pretty easy. We can just solve it directly. We have the inlet velocity is 0.2 meters per second. It's constant over the entire surface area. The surface area at the inlet is pi r squared, where r is equal to 0.02 meters or 2 centimeters. So 0.02 meters squared times pi gives you the area at the inlet 1.26 times 10 to the minus 3 meters squared. So the Q at the inlet is equal, the velocity times that area gives us this 2.51 times 10 to the minus 4 meters cubed per second. So that's the volumetric flow rate entering the nozzle. The same volumetric flow rate has to leave the nozzle. So in order to figure that out, we're going to look at U as a function of R. So we know that U0, that is U at the center of the stream, is some max velocity. It's not an amount we know, but we're going to call it U max. So that's the amount it is. And then we know that the U at the pipe edge, so I'm going to call that R out, is equal to 0. And that's what we said because of the no slip condition. So because the pipe is a solid substance, the fluid will have 0 velocity at the maximum R. And we know that we were told that U as a function of R is parabolic. So it has to go from 0 to U max in a parabolic way. That's kind of up to you to figure out what that function is, but once you've seen it, I'm sure you'll understand, and maybe in future life you'll be able to do it yourself. So that's our parabolic distribution that meets those criteria. So when R is equal to the maximum radius of the outlet, this 1 minus 1 goes to 0, and that gives you 0 velocity, no slip condition. When R is equal to 0, it goes to 1 minus 0, which gives you U max as the center velocity, the maximum velocity in the center. And finally, it is parabolic, of course, because this is all R squared. So that's a parabolic velocity profile. Now, we determined already in the prior lecture that the total Q dot out was equal to this integral of from 0 to the maximum radius of UR 2 pi r dr, where this 2 pi r dr was the dA, and this is our U. So we're going to be able to plug this UR into that and then take that integral, or at least that's our hope. Hopefully it'll be a solvable integral. So we have Q dot outlet is equal to the integral from 0 to the radius of the outlet of U max times 1 minus R over R out all squared times 2 pi r dr. U max is fixed, it's a constant, so we can pull that out of the integral. Obviously 2 pi is also fixed, so the Q out integral can be rewritten as 2 pi U max. It's good to get these things out of the integral just so you can see better what you're actually trying to integrate. I mean, if you have a whole bunch of terms in there, you can get kind of confused about what things are really being integrated or actually going to affect the integral, what aren't. So we've got now we've got R dr. So we really see the heart of the integral there. It's going to have some kind of cubic term in it, some kind of R term in it. It's not going to be a hard integral though, it turns out. So Q dot out is equal to 2 pi U max. All these things are constant times the integral from 0 to the outer radius of R minus R cubed over R out squared dr. So that's our integral, right? Everybody see that? So the R is multiplied through, give me R cubed, but this R out is only squared. So now I can take that integral, Q dot out is equal to 2 pi U max, and the integral is, of course, R squared over 2 minus R to the 4th over 4 R out squared evaluated at 0 and the maximum radius. Okay, then I can apply my limits of integration. Q dot out is equal to 2 pi u max times, I'm going to apply both limits of integration. So first I plug in R out. So I have R out squared over 2 minus R out to the fourth over 4R out squared. So that's the first limit of integration. Then minus the second limit of integration, but that's going to be 0 and 0. So that's just 0. So it's minus 0. So that's that. Obviously, these R outs, they're going to cancel a little bit. So I have R out squared in the numerator for both terms. So Q dot out is equal to 2 pi U max R outer squared times 1/2 minus 1/4. Well, 1/2 minus 1/4 is just 1/4. So Q out dot is equal to 2 pi U max times R out squared over 4. Well, obviously 2 and 4 are going to cancel each other. They're going to come up with 1/2. And I can plug in my R outer. I know what my R outer is. My R outer is, it's 1/2 of 1 centimeter. So it's going to be 0.005. So put this where you can see it still though. So R out is equal to 0.005 meters. And of course 2 divided by 4 is 2. So Q dot out is equal to pi U max divided by 2 times 0.005 squared meters squared. All right, so that gives me Q out is equal to 3.93. Sorry, that wasn't very well written. I'll just write it all again. Q dot out is equal to 3.93 times 10 to the minus 5 times U max. But now I can set that equal to Q in. Remember, Q dot in equals Q dot out. So Q dot in, we had way back before, was 2.51 times 10 to the minus 4 meters cubed per second. This has got meters squared units. And then that's equal to 3.93 times 10 to the minus 5 U max. This is meters squared. So U max is equal to 2.51 times 10 to the minus 4 divided by 3.93 times 10 to the minus 5. Those units are just the same, so you end up with 6.39 meters per second. Actually, one of these is meters cubed per. This one's meters cubed per second. So meters per second. Anyway, that's the answer. 6.39 meters per second is your velocity, the maximum velocity of the air as it leaves the jet nozzle in a parabolic jet. You are also asked to determine whether that was okay to treat as incompressible. Well, we know that incompressible is good till about 100 meters per second. So we're well below 100 meters per second, well below 0.3 Mach. So incompressible assumption is valid, and the maximum velocity is 6.39 meters per second.